This is section 3.3, day 2, for you to take notes on. And first thing we're going to do is kind of look at your homework from day 1. So if we look at this first function here, f of x equals 5, that's a horizontal line. So derivative or slope, so to speak, of a horizontal line is 0. For function 2 here, f of x equals 8. Again, a horizontal line, so the slope is also 0. And when I say slope, you're thinking derivative. Here for f of x equals 3x, the slope is 3, so the derivative must be 3. For function 4, which is 4x minus 2, it's a line with slope 4, so the derivative must be 4. And then 5, 6, 7, and 8, you were assigned one of those to do in class, the previous class time. And so the results from these last 4 were as follows. Function 5, x squared plus 4x, the derivative ended up being 2x plus 4 after you did the limit method. For 6, we ended up getting 6x minus 1. And for function 7, we ended up getting 3x squared minus 6. And for function 8, we ended up getting 3x squared minus 8x. So these last 3 are polynomials, and they tend to, they curve, so the slope changes depending upon the location of the curve. And these expressions are the expression for the steepness at any random given point. So if we look at the pattern here, what we discussed in class is that we see that this power of 2 ended up in front, and then the power on that term was reduced by 1. And so this next one here, function 6, if we bring the power 2 out in front to where there's already a 3, we had to multiply those together to get a 6. And then we can see that the power on this was reduced by 1. And then we can see on these next terms here, so that followed through with all these terms with powers. The x cubed, the 3 came down in front, right here, and the power was reduced by 1 to a 2. And same thing down here. Now if we look at the next terms, this linear term ended up just being a 4, in very similar fashion as to the reason why this derivative was just a 4. This is a linear term. The power up here is 1. We bring down the 1, multiply by the 4 to get 4. And if we reduce this power by 1, it goes to 0. And anything to the 0 power is just 1. So, so that the linear terms all had the same thing happen. This ended up being, its derivative ended up being minus 1. And the derivative for this term ended up being minus 6. And then the derivative for this term, if we bring the power 2 we multiply it by 4 to get 8. And then we have x, which is 1 power lower than what we had. So, so we recognized those patterns in class. And so we started to talk about them when we have these polynomial functions. We started to talk about a couple of the patterns we see. And one pattern we see is when we have a constant. For instance, when we had one of the functions 1 or 2, we ended up, that constant graphs a horizontal line, so its derivative or its slope is 0. So, for example, y equals 3. So this is kind of the beginning of your notes now. Y equals 3 is a horizontal line. The derivative or the slope of horizontal lines are 0. So its derivative, the derivative of 3 must be 0. And so we can say that really when we're being asked to find the derivative of function, the function's 3, we can think of that as being the slope of y equals 3. And so all constants have slope of 0 because all constants graph horizontal lines. So we just typically say this. This is kind of in the quotes here. It's kind of what we're thinking, but we say the derivative of 3 equals 0. This is not in your notes, but let's just kind of look at the general pattern here. We've done the derivative of x squared many times. If we use the limit method, we set it up like this. We do some simplifying and canceling, but we end up and I've omitted it here because we've done that several times. We end up with the derivative of x squared being 2x. Now, if we take a look at x cubed, we would set up the limit method like this, x plus h cubed minus x cubed over h. And we can do some, we can expand this and subtract that. And so I'm going to use Pascal's triangle to expand that cubic here. The Pascal's triangle gives me the coefficients for each term. So we have 1x cubed plus 3x squared h plus 3xh squared plus h cubed. So that's how we use Pascal's triangle to expand stuff quickly. Minus x cubed over h. And so simplifying, we can cancel out the x cubes, and then we're left with just the 3x squared plus x squared h plus 3xh squared plus h cubed. We're going to factor out an h and cancel that h. And then we're going to take the limit of this. So we put in 0 here and 0 here. We're left with just this. So we see that the derivative of x cubed is 3x squared. Okay, so we can start to see what happens with the powers and the coefficients as we do this. And we're just going to set up x to the 4th, again, not in your notes, but we have to expand this out to the 4th power, which is a lot of foiling, but we're just going to use Pascal's triangle to get the coefficients here. So expanding x plus h to the 4th power looks like this. 1x to the 4th power, 4x cubed h, 6x squared h squared, 4xh cubed, and 1h to the 4th. We wouldn't expect you to do this on a test, but this is just to kind of show you the pattern. Setting up the limit method, then we subtract x to the 4th, divide by h. We can cancel out, and we can factor out our h. I know I skipped some steps here. Oh, I think I had the steps below, actually. There we go. Here's what we have left. We can factor out an h and cancel that h. And then we're left to take the limit of this. And if we notice, we can put 0 in for these last terms here, and we're left with just the 4x cubed. So the derivative of x to the 4th is 4x cubed. So we can see this power coming down in front, and then the power being reduced by 1. So just to look at this pattern then, this is the pattern we're observing. X squared, if that's the function, the derivative is 2x. If the function's x cubed, the derivative is 3x squared. If the function does x to the 4th, the derivative is 4x cubed. So we can expand this now. X to the 5th is going to look like the derivative being 5. That's bringing down the power. X. And then reducing the power by 1 would be 5x to the 4th. And x to the 6th then is going to look like 6. That's bringing down the power. X to the 5th, reducing the power by 1. And so we can see that, we can start to see that pattern set up. And so we're going to call this then the power rule. And so taking the derivative, what happens, I call this a power reducer, because we start with a power n, and this is kind of the really mathy way. This is the way you would see it in your textbook. We bring down the power n, we bring down that original power, we multiply it by x to the power that is 1 smaller than n, which would be n minus 1. And so that's called the power rule. So let's look at some examples here. X to the 7th would be, the derivative would be 7x to the 6th. X to the 13th would be 13x to the 12th. And so this becomes, recognizing this power rule and this pattern becomes a real time saver, because it allows us to find the derivatives without using the limit method and without expanding out x plus h to the 7th or x plus h to the 13th. So it's a huge time saver rather than going through the limit method over and over. And so the nice thing is that the power rule works for any power. If we look at our powers right now, we've dealt with positive powers that are integers, so basically whole numbers. We can expand this though to negative powers and fractional powers, and so we're going to do that now. For instance, a negative power here, x to the minus 2, this is really 1 over x squared. But in order to do the power rule, we need to not have a fraction here. So x to the minus 2, the power rule works the same way. We bring down the power. So there's the power, we bring it down in front, times x, and then we've got to reduce the power by 1. So if we think about the number line, and that the numbers get smaller as you move to the left, 1 smaller than negative 2 is negative 3. So this derivative would be negative 2x to the negative 3. Now this answer's fine. You can leave it like this. However, most of these type of questions are multiple choice questions, which means you have to recognize the correct form of the right answer. And so usually we don't give answers with negative exponents. So this x to the negative 3 has got to be relocated to the bottom of the fraction so that we can raise x to a positive power. This negative 2 stays where it is because this negative sign isn't referring to a power. So this looks like negative 2x over x to the 3rd power. So this is how you would see the answer on a multiple choice. The constant multiple rule, we're just going to throw a bunch of rules at you here. The nice thing is we've discovered the power rule, we can see its pattern. The constant multiple rule, you've actually already been doing this intuitively. So this is not actually anything new. It's just been working out and you've been kind of integrating it right into what you do. So the constant multiple rule says this. If I have a constant, like this is a number, next to a variable, so let's think of this as like 7x, then I can take the derivative of that by putting the constant out front and just looking at the derivative of the x term. So let's take a look at this. So what we're going to do then is we're going to use the power rule, and we're just going to bring the power down front and multiply the two together, the existing coefficient and the old power, and reduce the power by 1 to get the new power. So this is kind of how it goes. If I asked you what 7x to the 5th, what the derivative of 7x to the 5th is, if I gave you a second or two to think about that, you would probably come up with the answer 35x to the 4th. You have just done the constant multiple rule in your head, okay? So like I said, you're already doing this. It's not anything new. The constant multiple rule is saying this. Take the 7 and bring it out front. That's the constant. Then do the derivative on x to the 5th. So bring the 5 down, write your x, and reduce the power by 1. So the constant multiple rule is just saying bring the constant out front and then multiply by the old power to get your new constant. So there's your 35x to the 4th for the derivative. Let's try this one. Not only does the power rule work for positive powers and negative powers, but it also works for fractional powers. So any radical can be written as a fractional power. I want to caution you, your notes might have a different fraction out here. If you could look at the example in your notes and change this to 3 over 5 so that your example matches what's on the video. So just take a second to look at that. I'll give you a second. Hopefully by now you've changed that so that this example in your notes says 3/5 times the square root of x. So now what we're going to do is we're going to take this radical and write it as a fractional power. So we have 3/5 x to the half power. That's what square roots are. They are half power. It's putting the root down in the bottom of the denominator here. So we're going to do the power rule here. We're going to take the 3/5 and move it out front. And then we're going to multiply by the derivative of x to the half. So we're going to bring down the power. The power is a half. So we're going to multiply by half times x to the negative a half. So subtracting 1 from a half, we jump over 0 and we get a negative a half. So this is the derivative. So I'm just going to clean this up a little bit and simplify it. 3/5 times 1/2 is 3 over 10. And notice what I did with the x to the negative half power. We know that the negative power will bring that term down in the bottom, and the 1/2 power is a root, so I've multiplied it on the bottom times the square root of x. So that derivative is 3 divided by the quantity 10 root x. So far we've gone over the power rule. It works for positive powers, it works for negative powers, and it works for powers that are fractions. We have another rule here. It's called the sum and difference rule. And remember, the sum and difference rule, the nice thing about this, just like the constant multiple rule, you've already done this. Okay, you're doing this already. So basically it's saying let's have something that has more than one term with separated by pluses and minuses. We're just going to take the derivatives one term at a time. And we can do that for adding, and we can do that for subtracting. And I know you only have one box to write this in, so maybe you want to write it as d dx of u plus or minus v equals du dx plus or minus dv dx. So it's basically just saying take the derivative one term at a time. So let's kind of take a look at this. For instance, here's an expression. It's a polynomial, it's a cubic, it's got 1, 2, 3, 4 terms, and we want its derivative. So when we want to find the derivative of this, we're just going to take the derivative one term at a time. So let's start with this first term, x cubed. The derivative is bring down the 3, x, reduce the power to a 2. So it looks like this. Bring down the 3, x, reduce the power to a 2, and then we're going to go to the next term. We're going to put our minus sign here. We're going to take the derivative of this next term by bringing down the 2, multiply it by the 3 to get a 6, x to the 1 power. So notice x to the 1 power. I didn't even write the 1. And then I'm going to put my minus sign here. And we're going to take a derivative of this, which would be just 6. And then the plus sign here can go away because the derivative of that is 0. So here's your derivative of that original function. And that is the sum and difference rules. That is just taking the derivative one term at a time. So let's find the derivative, and let's evaluate it at 2, 1 for this function. Now I'm throwing something that looks a little bit different, and we haven't had brackets yet, but this is easy enough to FOIL out, and that's exactly what we're going to do. So if we look at this, this is actually a parabola, and if we FOIL this out, you can see the parabola a little better. And 2, 1 is right here over 2 up 1. There's the location 2, 1. And so I need to take the derivative of this. So we're going to do the power rule on each one of these terms. So the derivative for 4x squared is 8x. The derivative for minus 20x is minus 20. And the derivative for 25 is 0. So we just didn't write anything after that. So that is the sum and difference rule. That's saying I have a difference in the sum, and I'm just going to take the derivative one term at a time. So now I have to evaluate this derivative. I want to evaluate it when the x value is 2, which means I got to stick the value 2 in here and come up with a number. So when I stick the value 2 in for the derivative, notice it's going into here, we get a derivative of minus 4. That means remember, when I say derivative, you're thinking slope. So that's the steepness of my curve at this location. So my curve is sloping down. That's why my derivative is negative. My slope is negative. And it's sloping down at a rate of 4. So now that we have the derivative or the slope and we have a point, we can write an equation for a tangent line. So there's my tangent line. I just went down 4, right 1. To draw that tangent line. I actually went left 1 and up 4 because that was on the graph. But now we have our slope and our point, and we're going to put that into our slope point formula. Remember, our slope point formula looks like this. So it's y equals, our slope value goes there, negative 4, x minus our x coordinate goes there, 2, plus, and our y coordinate goes here, 1. So this blue line has an equation of y equals negative 4 times the quantity x minus 2 plus 1. Now here's something that's a little bit different in its look. I want to know what the derivative of this product is. And so, again, I'm throwing kind of some brackets here, some parentheses at you. And if it's easy enough, what we want to do is we want to just do the math to get rid of the parentheses so we can just get back to that power rule. So multiplying this expression to get rid of the parentheses, we're going to end up with 14x to the 7th power. Now I've got a single term I can do my power rule on. So I bring down my 7, multiply by 14, end up getting 98x to the 6th power, reduce my power by 1. So there's my derivative. So that's how we can handle a pretty simple product here. But I want to look at this product and its derivative and see if we can find another way to do this. So let's take a look at this. and the wording here is important. The wording in blue here says, what is the derivative of this product? So notice we multiplied the product and then took the derivative. And now I'm asking this question, is this the same as the product of the derivatives? So is this the same as taking the derivatives first and then multiplying them together? So I'm swapping the process. This was multiply, then derivative. Now I'm going to do derivative, then multiply. So let's take a look at the derivative of this term. Bring down the 3, multiply it by the 7, 21x squared. And let's take a look at the derivative of this. 2x to the 4th, bring down the 4. 4 times 2 is 8. It should be 8x cubed. So here are my derivatives of each one of these. If I multiply these together, do I get 98x to the 6th? So when I multiply these together, 21 times 8, definitely not 98. It's 168. And x to the 2nd, x squared times x cubed is x to the 5th. So we do not get the right answer. We know this is the right answer, by the way. It's definitely the right answer. So if I just take the derivative of each and multiply them together, I don't get the right answer. So I can't do that. I can't just swap that process and get the right answer. But there is something I can do. And it's taking the derivative of each one of those expressions separately and then multiplying it by the other function, which sounds a little confusing. Let's just step through it. So we start by taking the derivative of the first. I'm going to call this 7x cubed. I'm going to call it the first expression, and I'm going to call 2x to the 4th the second expression. So we're going to take the derivative of the first, and that's our 21x squared. And I'm going to multiply that times the second. So I'm going to multiply this by 2x to the 4th. I'm going to take my 21x squared times 2x to the 4th. So this is the derivative of the first times the second. And that gets me 42x to the 6th. Well, at least I'm matching my powers now with the right answer. And now I'm going to swap that. I'm going to take the derivative of the second, which is 8x cubed. So the derivative of the second times the original function. So here's the derivative of the second times the first. And that's 56x to the 6th. If I add those together, notice I get 98x to the 6th. So in other words, I had to take the derivative one at a time. And the reason why I did is because I had to preserve this power. I couldn't reduce both powers at the same time. If I reduce both powers at the same time, then I end up with not enough power. So I had to reduce one expression's power, and then in a separate step, reduce the other expression's power. And that ends up giving us the right answer. So this process of, and watch my cursor, the 21x squared, this is the derivative of the first times the second, plus derivative of the second times the first. That process of taking one at a time gets us the right answer. And we call that the product rule. So let's take a look at what we did here. Like I said, let's call, 7x cubed, let's call that u. That's the first one. And this is how it's typically written. And then we're going to call 2x to the 4th, we're going to call that v. And so what we did then is we said, well, let's take the derivative of the first. So if the first is u, then this derivative is u prime. And then this derivative is v prime, because that's the second one. And so this is v prime. And so this then becomes u prime times v. And then we added them together. And this becomes u times v prime. And so this is the expression of the product rule. We take the derivative of the first times the second, and then we add to it the first times the derivative of the second. In other words, taking the derivatives one expression at a time. So we call that the product rule. And so that gets us then, if we add those products together, that gets us the right answer. So that is, now this is, we have a box for this. This is the product rule. And this is, we usually write this in prime notation because it's easier to write. Remember, this u prime is just basically du dx, and this v prime is dv dx. So that we use the prime notation because it's easier. So it's not just the product of two derivatives. So I want to really emphasize that. We tried that and it didn't work. We have to take the derivatives one at a time. And this is another way, a slightly different way of writing it. We just don't put in the dx. Not too important, but sometimes we see it like that. Okay, so let's try this now on this. Now this is not bad. We could FOIL this out. But we could also use the product rule. So let's take a look at this. FOILing it out gets us this. So we've got x squared, we've got 2x to the fifth. We've got 5x cubed plus 6x cubed and 15x. And we can combine it. And then we can take its derivative term by term, just like we were doing a couple of screens ago. This would be the sum and the difference rule. So we could take this, this would be 10x to the fourth, this would be 33x squared, this would be 15. But we could also do the product rule here. So we could take the derivative of this, which is 2x, and multiply it times this, and then add the derivative, or this first term times the derivative of this, which is 6x squared plus 5. So that would be the other way of writing that derivative. And if we did some distributing here, we could see that we have, as we go through here, if we look at this, x to the fourth, 6x to the fourth, and 4x to the fourth is 10x to the fourth. 5 and 10x squared and 18x squared is 33x squared and 15. So that ends up working out the same either way. So we're gonna this is the first exposure to the product rule. We're gonna keep working with this. And there are going to be expressions where this is definitely a huge advantage. We also have a quotient rule. This is harder to see. The quotient rule is when we have two expressions that are a rational expression, so they have a division sign in there. And the quotient rule says, let's take v times u prime. So in this situation, I refer to the u and the v as high and low. High is the numerator, low is the denominator. So this is low times derivative of high minus high, in other words, numerator, times derivative of low, denominator. And that's all over low squared. So this is what I think when I write this. I get my fraction bar out, and I think low, that's the v, it's in the low position, low times d high. D high means derivative of the numerator. Okay, so the d stands for derivative. So low d high is v times u prime minus high, that's the u, that's the top, times d low. D low means derivative of the low. Derivative of the low is v prime, all over low squared. So this on the top helps me remember this sequence, low d high minus high d low. It's just easier for me to remember. So let's try this with this expression. So low d high, so the derivative of this is low, which is this. Here's your low. D high is going to be 6x squared plus 5 minus high, which is just this. D low, so the d low is derivative of this, which is 2x, all over low squared. So that's how we use the quotient rule. Like I said, this is really tough to see, so it's harder to kind of put together an example. But these are typically multiple choice questions. So while this answer form is perfectly fine to put in for homework, on multiple choice questions, they always simplify the top. They don't touch the bottom. So once you have the bottom, your low squared, don't touch it. But the top should be simplified. So I'm going to FOIL this out and distribute this in the next step. So here's my 6x to the fourth, 6x to the fourth, plus 5x squared, plus 18x squared, plus 15. And then I'm going to distribute the minus and the 2x. So minus 4x to the fourth, plus 10x. And now I'm going to go ahead and combine terms. So 6x to the fourth minus 4x to the fourth is 2x to the fourth. I've got 5 plus 18, that's 23, minus 10x squared, which is 13x squared plus 15, all over x squared plus 3 quantity squared. So here's the derivative in its most simplified form. Notice again, I'm going to mention it one more time, we don't touch the bottom. We don't expand that out, we just put it as bottom squared. So at this point you have enough to do the day 2 homework. And this is again a 4-day section, so we're on day 2 of that homework.